Okay. Welcome to problem solving session for linear algebra. I'm Siddhi Balu Amburi from IIT Gandhinagar, and today we will discuss the topics linear transformation, rank nullity theorem, how basis affects the linear transformation, and the matrix of linear transformation. Okay. So we'll start with the first question, which will be related to linear transformation. So before we go to first question, let me define what is linear transformation for you. So let us start with the definition. So linear transformation. So if so let V and W be two vector spaces, then a map or function T from V to W is called linear transformation if T of V1 plus V2 is equal to T of V1 plus T of V2 for all V1, V2 in V, and T of C V1 is equal to Ct of V1 for all C in R and V1 in V. So we are considering V and W to be vector spaces over R. Then this is what a linear transformation is. And for this linear transformation, we have proved one lemma in the lectures, if you remember, that says that if that let T from V to W be a map or function between vector spaces V and W, then T is linear transformation. And when I say linear transformation, it means it should satisfy these two conditions, 1 and 2 are written above. So it is linear transformation if and only if T of V1 plus CV2 is equal to T of V1 plus Ct of V2 for all V1, V2 in V and for all C in R. Okay. So this is what a linear transformation is. This is the definition of linear transformation. So when we will be asked to check what is if some map is linear transformation or not, instead of checking these two conditions, we will be just checking this one condition and we will conclude whether T is a linear transformation or not. Okay. So let's start with our first question. So question 1, check whether the following maps are linear transformations or not. Okay, so let us start. So T is from R2 to R3 defined by T of x comma y is equal to x comma x comma x. Okay, so this is our map. So what we want to check? We want to check this condition whether if I take V1 and V2 in R2, so when so our V1 would be something of this form x1 comma y1 since we are in R2, and V2 will be x2 comma y2. Okay, this is an R2. And again, our vector spaces are over R. So let's see be any constant or any scalar from R. Then we want to check whether this T of V1 plus C V2 is equal to T of V1 plus C T of V2 or not. So let us start with our LHS of this equation. So T of V1 plus C V2 is what? T of what is V1? X1 comma Y1 plus C X2 comma Y2, right? So what is this T of X1 plus C X2? Y1 plus C Y2. And what this is? This is X1. So from the definition of T, we are just writing now the definition of T, that it is X1 plus C X2, X1 plus C X2, X1 plus C X2, right? I'm just writing the definition of this T here, okay? So we get this, and if I'm to separate this, what I will get? X1, X1, X1 plus C X2, X2, X2. And what this is? From the definition, it is T of X1 and plus C into what this is? This is T of X2, right? So what we got? Oh, T of not X1, T of X1, Y1 plus C, T of X2, Y2. Okay, and this is what we needed. And what is X1, Y1? This is T of V1 plus C, T of V2. Okay, any doubt here? So we just simply check this condition, T of V1 plus C V2 is equal to T of V1 plus C T V2 or not. And here we got it. Any doubts here? Okay, so I assume there are no doubts. So we'll move to our second question. Then again, here also we want to check whether given linear given map is linear transformation or not. So we are in P3R. So P3R is set of all polynomials in variable x of degree 3 or less, and P4R is again polynomial in degree 4 or less in variable x. Okay, and our map is now defined by T P of x. So where here P of x is in P3R, and it is integration from 0 to x pt dt. Okay, so this is our map now, and we want to check like this map is linear transformation or not. So to proceed further with the question or and directly solving this condition, we would first like to see like how T actually looks like. So let us write this P of x to be a1 x cube plus a2 x square plus a3 x plus a4. Okay, then what is T of px will be? It is integration 0 to x a1 t cube plus a2 t square plus a3 t plus a4. Okay, and dt. And when I integrate this, what I will get? A1 t power 4 by 4, A2 t cube by 3 plus A3 t square by 2 plus A4 t. And this is, I need to evaluate between 0 and x. And when I evaluate this over at 0 and x, I get that the zero term will be always, everything will be zero because here I have t everywhere. So when I substitute t to be zero, I will get zero. So finally I remain with a1 x power 4 by 4 plus a2 x cube by 3 plus a3 x square by 2 plus a4 x. Okay, so this is how my t looks like. Okay, so now I will go with our condition like let P of x and Q of x, let Q of x be in P3R and C be any scalar, then T of Px, and let me write Px, is a1x cube plus a2x square plus a3x and plus A4 and QX be B1 x cube plus B2 x square B3 x plus B4. Okay. Then this T of Px plus CQX will be what? It will be just, let me write it. This is was T of A1 plus CB1 x cube plus A2 plus CB2 x square plus A3 plus CB3 x plus A4 plus CB4. Okay, so I'm just writing what is this P plus CQ is. And now I know like how it look like. So it is just A1 plus CB1 x power 4 by 4 plus A2 plus CB2 x cube by 3 plus A3 plus CB3 x square by 2 plus A4 plus CB4. Okay, is this okay for all right now? So I'm just evaluating the map T at this element PQ plus CQX. Okay, and now I want to check the RHS, which was what? T of Px plus C T of Qx. And when I do this, I get what? A1 x cube, sorry, x4 by 4 plus A2 x cube by 3 plus A1 x square by 2 plus a f not this was A3, this is A4 x plus just a second C into B1 x4 by 4 plus B2 x cube by 3 plus B3 x square by 2 plus B4x. Okay. And when I take all the coefficients together, I end up getting A1 plus CB1 x power 4 by 4, A2 plus CB2 x cube by 3. Let me write it below. A3 plus CB3 x square by 2 plus A4 plus CB4 x. Here it was x. Okay. So if you check this, if I call this 1 and if I call this 2, then 1 is clearly equal to 2, right? These two terms are same, this and this. So we get that, therefore T is a linear transformation. So far the two maps which we checked were linear transformation, okay? Any doubt here? So I simplified this just to get hold, because every time integrating in between the polynomials would be difficult sometimes. So I just saw like how this linear transformation look like, how this P of X is going to. So, and I just got this expression that T of P of X is this thing. Let me draw this box. Okay. So I hope this is clear. If you have any doubt, please write it in the chat or unmute yourself and ask. Okay, so I'm moving to the third question, and we will check whether this is linear transformation or not. So, or since I'm writing it like this, third one is T from R2 to R2 defined by T of X comma Y is equal to X square comma Y. Anybody want to guess whether this is linear transformation or not? What is your guess for this map? Whether this map is linear transformation or not? It's not linear transformation. So, okay. So as Divya said and Karthikeyan said, these are not, this is not a linear transformation. So instead of going to, so since we have that it is not guesses that it is not a linear transformation, let me quickly just write that how what will happen. So I'm just writing it directly, that c y1 comma x2 plus c y2. So this is how, if I take where x1 comma y1 in R2, x2 comma y2 in R2, and c in R, then this will be what? This will be x1 plus c y1 whole square comma x2 plus c y2. Okay, or x2 y1 x cx2 y1. Okay, and what is t of x1 comma y1 plus c t of x2 comma y2 is? It is x1 square comma y1 plus x2 square cx2 square comma y2, and this is what? X1 square plus cx2 square and y1 plus c y2. Okay, but clearly, I mean, we can see that there are examples for x1, x2 and c's where this does not hold. So for example, in particular, if we choose x1 comma y1 to be 0 comma 0 and x2 comma y2 to be 1 comma 0 and c to be 2 in R, then what this will be? The first term, and this, let me call this second term, then first term will be what? It will be 0 plus 2x, right? 0 plus 2. So it will be 2 square comma 0. So this will be 4 comma 0. And what the second term will be? It will be x1 square. x1 is here 0. So 0 plus c is 2 and x1 square. So 2 into 1 square comma 0, since y terms are 0. So I will get now what? 2 comma 0. And this is clearly not equal. So clearly this is not a linear transformation. So any doubts here? Like those who couldn't predict that this is not a linear transformation? Okay. So I guess that all of you got the idea. I mean, this is not the only examples. You can simply also do the adding part, where you can choose 1 1 and 1 plus 1 square will be 2 and 1 square will be 1 1, and then you will get 2. So that would also work. So first coordinate is a problem here. Okay, so because x going to x square is not a linear map in general, so that's why this is happening. So this was the example where the t was not a linear transformation. So let me write it. Therefore, t is not a linear transformation. Okay. If you have any doubt, please let me know. If not, then we'll move to the fourth question. Here we have t from M to R to R. So this is set of all 2 cross 2 matrices over R map, and it is mapping to set of real numbers, and we define that T of A is equal to trace of A. Trace of A is addition of diagonal entries. So, okay, A in, okay. So we want to check whether this is linear transformation or not. So what is your guess in this case? Will this be linear transformation or not? Yes, so Jackie said that this is linear transformation. Okay, so we will do the quick check. So let A be A I J I comma J from 1 to 2. I hope you remember this notation. This is just I am writing a shorthand for the matrix. So this is actually A11, A12, A21, A22. Okay, and similarly for B. And let C be a scalar from R. So consider this T of A plus CB, and what this will be? T of So when I add this, I will get this matrix Aij plus C Bij I comma j from 1 to 2. And the trace will be addition of just the diagonal entries. Okay, so addition of diagonal entries will be what? A11 plus C B11 plus A22. So here, see the notations or the subscripts where I and j are equal are the ones in the diagonal. So A22 plus C B22. Okay, so and let me just shuffle them here itself. So what I will get A11 plus A22 plus CB11 plus CB22, and this will give me A11 plus A22 plus CB11 plus B22, and this is what? This is T of A, because this is what? Let me write trace of A plus C into trace of B, and which is nothing but our T of A plus C T of B. So this is what we needed. Yes, even Divya also said that this is a linear transformation. Okay, so as we saw that this T is a linear transformation. So the lemma which we proved in the lectures was important. So instead of checking the two conditions of addition and scalar multiplication, we have combined them and obtained that this T of A plus CB giving us TA plus CTB is enough to conclude that T is a linear transformation or not. And the final of this kind, like where we will be checking that whether T is a linear transformation or not. So let us again, we have this T from set of 2 cross 2 matrices to set of real number, and now we are considering T of A to be determinant of A. Okay, so this is determinant of A, and your guesses, any guesses whether this will be linear transformation or not? So any guesses?
No.
Okay, this is okay. So Veda said, I guess, that this is not a linear transformation. Okay, so can somebody give me a quick counter example? I mean, we also learned this last time where we wanted to check that set of all matrices where determinant equal to 0 is subspace of a given vector space or not. And there we had given a example where the determinant of matrices were 0, but when we were adding them, the determinant was 1. Okay, so we will try to construct such a matrix here, because in general, this statement T of A plus CB is equal to T of A plus C, or let me write this. Determinant of A plus CB is not equal to determinant of A plus C determinant of B. And to consider this, we can take C to be 1, A to be this matrix 1 0 0 0, and this matrix B to be 0 0 0 1. Okay, then determinant of A plus CB will be determinant of just A plus B, and A plus B here is our 1 0 0 1. So it is identity matrix, and we know that determinant of this is 1. And but what is determinant of A plus C determinant of B? This is what? Determinant of this matrix A, which is 0, determinant of B, so 1 into determinant of B, which is 0, then we are getting 0. So these two are clearly not equal. So therefore, here T of A plus CB is not equal to T of A plus CT of B. Therefore, this T, that is a matrix owing to its determinant, is not a linear transformation. So T is not a linear transformation. Okay. Any doubts here? So in general, a determinant is not a linear transformation, because this main property, that determinant of A plus CB need not be equal to determinant of A plus C determinant of B. Okay, please check this. And I mean, I have explained. If you have any doubts, please ask. So this is not linear transformation. Okay, no doubts. Great. Okay. So now the next question which we will be discussing are more or less related to that how a basis in the vector space of a codomain uh, goes to, I mean, how the corresponding elements under a transformation works in the codomain vector space. I mean, you will understand when I will write the question. So so we have to check whether true or false the following statements. Uh, so the given setup is that V and W are vector spaces and T from V to W is a linear transformation. So we are already given that T is a linear transformation. So we need not worry about checking all the conditions here. So T is given to be a linear transformation. And now the first statement is that if B is this basis, Vm be a vectors in V such that, okay, so B is just a set of vectors, but TB is what? TV1 corresponding images, set of corresponding images of B is a set of M linearly independent vectors. Okay, so we are given that this image, the TB set, is linearly independent in W. Okay. Then our question is that B is a linearly independent or not. So they are saying that if TB is linearly independent, what can we say about the B? That is the question here. And they are they are saying that it is linearly independent in V. So what is your guess for this? If a V is a linear transformation, T is a linear transformation and B is any set of vectors in V, and TB is a set of vectors in W such that TB is now linearly independent set. So what can we say about linear independence of B? Any guesses? Okay, so Divya said that it is false. Okay. Any other guesses? Jackie is saying that this is true. Okay, so we have two different or opposite guesses. So let us start. So we want to, so what is here to check that whether B is linearly independent or not. And how do we check that? We start with the linear combination in in V of this V1 to Vm, and then we will go. Okay. Okay. So Veda is saying that, I guess, that if B is linearly independent, then TB is linearly independent. No, but we are asked the other way around. That if TB is linearly independent, can we say that B is linearly independent or not? That is the question asked here. Okay, so we will check. Okay, so we want to check whether B is linearly independent or not. So let us start with it. Okay, so let A1 V1 plus AM VM be 0. Okay, so we want to check that it is linear transformation or not. So we start with the linear combination. If T is 1, 1, it is true. Okay. But here we are not given such condition. T is just a linear transformation. Okay. The condition on T is here that V and W are just vector spaces and T from V to W is just a linear transformation. We don't know whether it is 1, 1 on 2 or other things. So let us start. Okay. So we have this linear combination of V1 to Vm and we want to check whether the coefficients are all zeros or not, or we are getting any linear combination where this is not zero, and so on. So we have this, right? So V1 to Vm is 0 and T is a linear transformation. So we know that T of 0 goes to 0, right? So T of, this is what 0. So A1 V1 plus AM Vm will be 0. And now this V is in V and sorry, this 0 is in V and this 0 is in W. Okay. So I'm just clarifying it. So what this is, so T is again linear transformation. So I can write this term as A1 TV1, A2 TV2 plus AM TVM, right? And this is now this. But what I know that this set TB, so these are elements from TB and TB is linearly independent set. So what does this imply? A1 is 0, A2 is 0, so on, AM is 0. And why? Since TB is linearly independent, okay? So we started with this linear combination of V1 to Vm with some coefficients and we end up getting all the coefficients to be 0. So what we get? V is what? I mean, B is what? Linearly dependent or independent? We started with a linear combination and we got all the scalars are linearly independent. All the scalars are 0. So as Karthikeyan said that this will be, therefore this B is linearly, okay, linearly independent. Okay. So is it clear now that we had this V set, but its image is linearly independent? So the state set from which we started, the B, now has become the linearly independent set. Any doubts here? If there are doubts, please write. And those, just a second, let me check who are there. Yeah, Divya, do you got that this is true statement, okay? That it is linearly independent statement. And also those who were guessing that B is linearly independent, then TB and so on. Please understand that TB is given to be linearly independent and B now we have got is linearly independent set. So yes, so there are no whether converse is true. Okay, so we will check that in next question that whether the converse is true or not. We are actually getting towards it. So let us start this. Okay, the converse need not be true. Okay, let me just tell you that. Converse is not true in general because we being linearly independent, we need not have that TB will be linearly independent. We will see a example in next few minutes. Okay. And meanwhile, you can just think of it, what can be a example or counter example for this thing. Okay. So the next question is we have to check whether the image of a spanning set of V under T is spanning set of W. So we have to check whether so this statement is true. Okay, let me write this. This statement is therefore true. Okay. The image of spanning set is spanning set under T. So if we have spanning set, let me write this B itself again. Suppose V1 to Vk is spanning set in V, then the corresponding TV, which is TV1, TVK, whether is spanning set in W or not. Any guesses here? No, Veda, what you said is not true because One side we proved that if TB is LID, then B is, when you are writing LID, I assume that you are talking about linear independence. So if TB is linearly independent, then B will be linearly independent. But the other way is not true. That if B is linearly independent set, then TB need not be linearly independent set. For example, just understand that if I take zero transformation is also linear transformation, right? And then if v1 to vk all to be non-zero vectors, linearly independent vectors maybe, but T of B will be what? Everything will be 0, 0, 0, 0. And once we have 0 in the set, it becomes linearly, there is no thing to be checked whether it is linearly independent or not. Zero set, a set containing 0 is linearly dependent because, yeah, exactly. So because we can always take non-zero coefficient and any non-zero into 0 will be 0 in the set, okay? So this statement is not in general true. So we will see. So for spanning set, so we are at the spanning set. Any guesses here that if B is a vector space, sorry, B is a spanning set of V, then what can you talk about the spanning set of B in W? It is false. Okay, Jackie's guess is it is false. Any example? Again, we can take the linear transformation 0 as I said, okay? So let V be R2 and W be again R2. You can take any non-zero, so W, any non-zero you take. Okay, then T from V to W, I'm taking all the V's are going to 0 set. Then T, so let V be any spanning set or let V be basis of our usual basis of or standard basis of R2. But T of B is what now? X comma Y going to 0 comma 0. It is just 0 comma 0, 0 comma 0. And this is definitely not spanning set of R2. Okay. Any doubts? Yes. Again, Veda also guesses that this is not true. So this is not a spanning set. Okay. Zero transformation will always mess up with the span of the set and also the linear independence. Okay. And next question is exactly the combination of both of them. And next question asks me, so this is false. Okay. This statement is false. So if let B is equal to V1 to Vn be basis of V, then TB is again, we all know that is a basis for W. So your guess, any? There is nothing to guess, right? We just already discussed that this is false and we can take W any non-zero vector space and T to be a zero transformation. I hope you understand what zero transformation is. Everything is going to 0. Okay, but just because we need not always rely on zero vectors, zero transformation. Okay, so let me just give you one quick example. Quick non-zero, like non-trivial transformations where these conditions hold, the spanning and the basis one. Okay, so we can consider this T from R2 to R3 such that x comma y is going to x comma y comma 0. Okay. Then B, if I take standard basis of R2, but then TB will be what? 1 comma 0 comma 0, 0 comma 1 comma 0. Now, is this a basis of R3? Any guesses? I mean, Is this basis of R3? This is not basis of R3, okay? This is not basis. Yeah, Jackie said that this is not a basis of R3. And why not basis? Because TB does not span. Okay, yes, exactly. Jackie said that this does not entirely cover R3. So this does not span R3, okay? So this is not trivial example for spanning. So we can also use the same example here also, that TB is not a spanning set for R3 and we need not have the zero map. And once again, I would like to give this example as well, R3 to R2, x comma y going to x comma y plus, oh sorry, we are in R3. So x comma y plus z going to x comma y plus z. And then again I take usual basis or standard basis of R3, 1 comma 0 comma 0, 0 comma 1 comma 0, and 0 comma 0 comma 1. Then TB will be what? 1 comma 0, right? This will be 0 comma 1 and 0 comma 1. And is this basis? Is this basis of R2? No. And the reason being LD. Exactly. Because now TB is linearly dependent here. Okay. So linear zero transformation is always helpful, but we also should know that this actually happens. That the spanning set need not span to spanning set, and linearly independent set need not span to linearly independent set. Okay. Any doubts here? Like what is happening, how is happening, or anything you're not clear with definitions or anything? Please let me know. I will clear it. Just look at this example. Any doubt, please let me know. Okay, so no response. So I assume that you all understood. So let us move to next question. Okay, let me use neighbors. So the linear, again, we have to check whether true or false. The linear transformation T is injective if and only if the only vector V in V such that TV is equal to 0 is the zero vector. What is your guess? Whether this is true or false? So this one was false. I already wrote that. Okay. Any guesses for here? That they are saying that T is injective if and only 0 is the only vector such that TV is 0. The TV is 0 means what? T of V is 0 under this linear transformation. Any guesses? Whether this is true? Okay, Jackie said this is true. Okay. So yes, everybody is saying Karthikeyan, Veda, everybody is saying that this is true. So let us try to prove this. Okay, this is if and only if statement. So we have to prove the both the sides. So first side that given that T is injective linear transformation, we have to check that the only vector such that TV is 0, then V must be 0. Okay, even okay. Everybody is saying it is true. So let us start. T is injective and then what does this mean? What does this mean? That TV1, the definition of injectiveness. TV1, that is TV1, TV2. I mean, if image of two vectors V1 and V2 are same, then V1 has to be equal to V2. This is the definition of linear transformation. Sorry, injective map. Any doubt here? This is the definition of injective map. Then we know that T of 0 is 0 because T is linear transformation. So 0 goes to 0. This is all we know. Then if we have any other V1 in V such that T of V1 is equal to 0, then what does this 0, but what this 0 is? T of 0. Okay. So from this, let me call this star. So then this gets what? V1 is actually 0 from star. So if we take any vector such that TV is 0, we end up getting that this V1 is actually our 0 element. So therefore, 0 is the only element such that TV is equal to 0. Okay, any doubts here? I'm just using the definition of injectivity and the fact that 0 goes to 0 because we are having T to be a linear transformation. Okay, so T is a injective linear transformation and I'm just following the properties of injectivity and the T being linear transformation. Any doubts, please let me know. If not, we have to prove the other direction. And now for the other direction, we are giving that 0 is the only element such that T of 0 is 0. Okay, T of V is 0. So suppose T is not injective, okay? And when I say this, what does that mean? There exists V1 not equal to V2 such that T of V1 is equal to T of V2. Okay, then what does this imply? So since V1 is not equal to V2, this implies V1 minus V2 is non-zero, right? Such that this is linear transformation. So T of V1 is equal to T of V2 implies T of V1 minus T of V2 is equal to T of V1 minus V2. And this is what? 0. Because we are given that T of V1 is equal to T of V2 to be 0. Or let me write this is equal to 0. Therefore, this is 0. So we got that V1 minus V2 is non-zero, but T of V1 minus V2 is 0, which is contradicting our given condition that 0 is the only element such that T of V is 0, right? So this is contradicting our given condition here that 0 is the only element such that TV is equal to 0. Okay. So therefore our supposition is wrong and that is T is injective map. Any doubts? This was quick proof of these two things. That 0 is the only element going to V, then T has to be a injective map. And this you can keep in mind as a theorem or corollary or statement where if somebody asks you to check whether a given linear transformation is injective or not, you just check whether what a null space of that linear transformation is. If it is only 0, then we can say that it is a injective map. Any doubts? Okay, no doubts. Great. So this was related to how basis and the spanning set goes to under linear transformation. And now we will move to the third topic, which is related to rank nullity of the given transformation. So let us quickly go through what is null space, what is nullity of transformation, and what is rank and range of a transformation. So let T, let V, W be vector spaces. Then, and let T from V to W be a linear transformation. Okay. Then null space denoted by null of T is set of all V in V such that TV is 0. Okay. And this is contained in our V. And this is in fact, if you check, this is subspace of V, and dimension of this null T is called as nullity of T. Okay. So dimension of null space is called as the nullity of T. And now something, the range of T. Any doubts? I mean, this is just the definition. Something being null space, and the dimension of null space is called as the nullity of T. And range of T is the set denoted by RT, and it is what? It is all the TVs such that V in V. Just recall myself, dimension means number of bases. Yes, dimension means the number of bases. Yes, definitely. Dimension means the number of bases. So null space is a vector subspace of V. So we have to find the number of bases, and that is dimension. Yes. And TV. Okay, it is contained in W, and it is in fact subspace of W. And now this dimension of R of T is actually called as rank of linear transformation T. Okay. So this was just, I was recalling definition if any of you could not go through the lectures. Okay, so I hope these definitions are clear. We have to, so this, when we talk about nullity, we are talking about the dimension of the subspace inside V. And we talk about the range, we are talking about the dimension of subspace inside the W. So let us, so based on this nullity and rank, we have this dimension theorem, which we will be using in upcoming questions, that let V be a finite dimensional vector space. So V being finite dimensional is important. And T from V to W be a linear transformation. Then what they say, that dimension of V is actually rank of T plus nullity of T. And this is also known as rank nullity theorem. So this is the theorem which we have. So dimension V, so V is finite dimensional vector space, so it will be some number, and what it will be equal to, it will be rank of T, that is dimension of range set, range space of T, and nullity of T is rank of the, or the dimension of null space of T. Okay. So keep this in mind. The dimension of V is equal to rank T plus nullity T, because that's what we will be using. So our next question is, just a compute the rank. I think this was question 3. Compute the rank and nullity of following linear transformations. So we are already given that something is a linear transformation, and we want to check, or we want to find its rank and nullity. What is the first question? T from R2 to R3 defined by T of x comma y going to x comma y comma x plus y. Okay, so we have to find first the nullity. Okay, that is first we find the null space of T. So what this is x comma y in R2. So nullity is always subset or subspace in V in the domain. Okay, so such that T of x comma y is equal to 0. And what does this mean? And what this gives me? That x comma y in R2 such that x is 0 and y is 0, right? When I write T of xy is equal to 0, it means it is 0, 0, 0. And this is what we get from the first two coordinate itself. And x plus y is 0. The third condition is also satisfied here. Okay. So what this is? This is 0, 0. So nullity of T is what? Dimension of null space, which is just a 0, 0. So it will be 0. Okay. Any doubts? Yes, it means T is injective. Yes. Because, and you can clearly check that it will be injective. Yes, recalling from the previous theorem. So T is injective and so we have nullity and dimension of R2. So dimension of V is what? Dimension of R2 here. And what is dimension of R2? It is 2, right? So from rank nullity theorem or from dimension theorem, what I get? That dimension of V is equal to nullity of T plus rank of T, right? So what this will give me, that 2 is equal to nullity of T is 0 here and rank of T is what? We will get it. And from here, we clearly get that rank of T is actually 2. Any doubts? We just obtained we found the null space, took its dimension and used the dimension theorem and got that rank of T is 2. Any doubt how we did that? And please understand this. We are just comparing these first two coordinates here. This one with this one and this one with this one. And we already got 0. And the third coordinate also, as I said earlier, we need to check whether it is true or not. And in this case, since x, y and y are 0 and x plus y is again, when we compare to the third coordinate, it will give me 0. So this is giving us null space is just 0 element and nullity T is 0 and dimension of vector space is 2. So rank of T is 2. So moving to next question. Any doubt, please write it in the chat. Okay, so now next linear transformation is from P3R to R defined by TP is equal to P of 0. So TP is equal to P of 0 means when we evaluate the polynomial P at 0, whatever we get is our image under this linear transformation. So how to do it? So null space of T again we are finding, and it is what? All the P in P3 are such that T PX is equal to 0. So this is what P in P3 are such that P of 0 is 0. And when I write this P of 0 is 0, what we mean is, so if I write this P to be, what I'm writing? Okay, P3x cube plus p2x square plus p1x plus p naught, then what I will get is that p3 0 cube plus p2 0 square plus, yes, constant term of the polynomial becomes 0, as I hope, plus p0 is equal to 0, and what I get that, so note that all these coefficients here, I take any numbers for p1, p2, p3, I take any number, it will always end up adding up to 0. So only thing we need to take care of is p naught. And for this sum to be 0, we must have p naught equal to 0. So the polynomials we get here are such that p naught is 0 and p1, p2, p3 or p3 in R. Okay. So these are all the polynomials of the form p3x cube or p3x cube, p2x square plus p1x belong to p3R. And what is dimension of this set? The dimension of nullity, anybody wants to guess? Yes, Jackie said 3, even Abby said 3. So it is 3. Okay. And from rank nullity theorem, so I am in P3R. So dimension, so here V is my P3R. And the dimension of P3R I know is what? So basis for P3R is 1x, x square and x cube. This is standard basis of P3R. So dimension of P3R is 4. Okay. So from dimension theorem, what I will get? Dimension of P3R is equal to nullity of T, or nullity of T. Oh, this is all like this. Nullity of T plus rank of T. And nullity is what we got? It is 3 plus rank of T, and here it is 4. So what we get from here is that rank of T is 1. Okay, any doubts here? Understand this thing, okay? That taking any coefficients of x square and x cube in P will always give us 0 when we evaluate it at 0. The only thing which would create problem is P0, the constant term. So we have to make it to 0, and then all the rest coefficients of P3 with respect to x square and x cube could be anything from R. So that's how we get the null space, and it becomes that nullity is 3, and by using dimension theorem we get that rank of T is 1. Any doubts here? Okay, so no response, so I assume there are no doubts. Yes, please ask. Yes, that is the last question which we will be discussing. The transformation, okay, the matrix to find transformation. Yes, we can do that. That's not a problem. We can find the matrix of the transformation, and we can check rank of it, and whatever dimension is, we will get. So the rank, so using null space, we are getting the dimension of, we are getting nullity. Using the rank of a transformation matrix, we will get the rank of transformation. I mean the rank of T. Yes, you can do that. So this is the last question in this note. That, okay, great. Uh, which one is it? Okay. that we will be finding rank and nullity. So M2 going to M2R defined by, so we are in 2 cross 2 matrices over R such that T of A is A transpose. Okay, T of A is A transpose. I hope you know what A transpose is. I will just write it, you will get an idea. Then now what will be null space of T? It is all those A in M2R such that T of A is equal to 0. And when I write T of A is equal to 0, I mean A transpose is this 0, 0, 0, 0 matrix. And what does this give me? A11. So if I take A to be A11, A12, A21, A22, then A transpose is A11, A21, A12, A22. Okay. And this is now what? 0, 0, 0, 0. And what I get here is everything is 0. All the coefficients or all the coordinates of matrix are 0. So again, what we got here is it is just a 0 matrix, and therefore nullity of T is 0 here. Any doubts? And again, using dimension theorem, here dimension of M2R is 4. So therefore we get dimension of M2R from dimension theorem is equal to nullity of T plus rank of T, and we get 4 is equal to nullity is 0 plus rank of T. So this will give me rank of T to be 4. Any doubts? Any doubts here? This was quite quick because we immediately got everything because null space was just 0 element. Okay, so but matrix 2 cross 2, right? Then how rank? Okay, so it is okay. So rank of a transformation is 4. So when you write the map of this linear transformation, it will be 4 cross 4 matrix. Because dimension of M2R is 4. Yes, transformation is from 2 cross 2 to 2 cross 2. So it is 4 cross 4 matrix. Because how you will write the transformation? Transformation matrix is, so we will go to transformation matrix in few minutes. Okay, got it, right? You yourself understood. So it is corresponding to each basis element. We write the coefficients in the codomain element, and then we mix them, and then we get the transformation matrix. I will explain it in few minutes. And there I will also give an explicit example of how to calculate a linear transformation matrix and so on. So it is obtained from the coefficients of the basis elements. So that's why it is 4 here, because M2R has dimension 4 and the codomain also has dimension 4. Okay. So it will be 4 cross 4 matrix. So this is next question. Which question we are on? Fourth. Okay. So we have this setup for this question, that for each matrix A in M2R, we define this map. So they are saying that it is a map and not a linear transformation. Okay, this is just a map defined by TA of B is AB. So A is 2 cross 2 matrix, B is again 2 cross 2 matrix. So we are multiplying the matrices. Okay. So we want to check whether the following statements are true. True or not under this setup. Okay, so first thing they are asking to check is that TA is a linear map or not. So when we say that it is a linear map or not, they are asking whether TA is a linear transformation or not. So what is your guess that whether TA is a linear transformation? Any guesses? Yes. So there. So I think AB or AB or E said that TA is a linear transformation. So let us start that if B comma C is in M2R, okay. B and C be M2R, and let R be our scalar, and we have to check whether TA of B plus RC is what? A into BA plus RC, right? And what is this A? B plus A RC. And what is A into RC? It is just RAC, okay? Yes, you can check this. This is 2 cross 2 matrix. So let me just quickly A1, A2, A3, A4. And what is RC? It is RC1, RC2, RC3, R RC4, and this will, you can clearly see that this everything will have R coefficient every term, and we can take just R common, and it will be A1 C1 plus A2 C3 and so on. And we can now take R common, and the element inside the matrix are just AC. You can just quickly go through it. This is just this matrix. And what is this? AB is what? TA of B plus R, TA of C. Okay, any doubts here? So therefore, it satisfied the condition which we were so far looking for, linear transformation. Therefore, this TA is linear transformation. So we can define the linear transformation like this, that take any matrix and we can just take matrix multiplication with respect to that matrix, and the resultant map is a linear transformation. Any doubts here? No. Okay. Second in this same line is that the cardinality of set, let us call that set to be F, A in M2R, such that TA is 0 is at least 2. Okay, it's at least 2. What does this set means? First of all, so this set is A in M2R such that TA is 0. And when I'm writing TA is 0, it means, just a second, it means that TA of, since we are in matrix set, is 0 for all B in M2R. So it is actually zero transformation. They are asking that there exists, what they are saying that there are two matrices corresponding to which we have zero linear transformation. And as Karthikeyan said that this is not true. Okay, this is not true because we will just see that why this is not true, such that AB is equal to 0 for all B in M2R. And any guesses why this is not true? I mean, how can we say that this is not true? So first of all, we know that clearly zero matrix, I mean this 0, 0, 0, 0, this belongs to S. That is not a doubt. Zero matrix multiplied by any matrix will give me 0. So corresponding to zero matrix, so that is this T0, 0, 0, or let me write T0 is a 0. That's not a problem. Okay, so let A be any non-zero matrix, or let me write it this way. Let M2R such that TA is 0. Not injective. I mean, what is not injective? I mean, no, we are not talking about the injectivity of the map here. We are saying that this set corresponding to which the linear transformation is entirely a zero linear transformation. We are talking about those sets. We are not now checking the, what I can say, null space. I'm not talking about the null space here. I'm just considering this set S of the matrices A such that TA is 0. When I write this TA is 0, I'm saying that this corresponding map, that TA from M to R, oh, let me write this figure. This TA from M to R to M to R such that B going to AB, whether this is always giving me 0 or not. So I want to find all these A's here. We are not checking the injectivity of the map TA, because I'm looking for the A's for which this map is giving me the 0 map. Okay, so you will see that suppose that this A is non-zero. Okay, so A is non-zero matrix, and we know that I means this matrix, identity matrix, belongs to M2R. So if TA is 0 map, then this A into identity will be 0. But this is not true, which is not true because A into I is A, and which we have already assumed to be non-zero. So therefore, such A does not, non-zero A does not exist. Therefore, cardinality of S is exactly 1. Therefore, given condition is false. Any doubts? They're asking us that the which matrices will give me the zero transformation if I define the corresponding linear transformation, this TA. Any doubts? I know this statement is a bit confusing because now I'm talking about this set S. But yeah, I'm looking for the matrices which are giving me the zero transformation in general. Any doubts? Jackie, any doubts do you have, or is it clear now? I'm not talking about TA being injective or not. I'm just looking for the matrices which will give me zero map. Okay? Okay, great. So you got it. So we'll move further then. And now the linear transformation matrices which we would like to see. Let me start with the new page. So what is linear transformation matrix actually, or the matrix? So what we are talking right now is that if T from V to, okay, let V and W be vector spaces, or let them to be finite dimensional, then let T from V to W be a linear transformation. Okay. Then the matrix on let beta be vector space or basis of V1 to Vm, and gamma be W1 to, let's say, Wn be basis of V and W respectively. Then the matrix of linear transformation, okay, T is this matrix T, what I'm having this beta and gamma, and how this is obtained is actually I'm taking this T of V1 here, T of V2 here, up to T of Vm here, and I will, so now this T of V1 to Vm are in what? Are now, these things are now in W. And W has now what? This basis gamma. So what I will take? Corresponding linear combinations, okay, of this TV1 in terms of Wi's. And the corresponding coefficients, I will write it, the coefficient of W2, coefficient of W1, W2, up to coefficient of Wm. And this resultant matrix is now O and N cross M matrix. Okay. So this is how we get the linear transformation matrix with respect to any basis. We will see the explicit examples here, and at the end I will also explain you like what is the significance of this uh, linear transformation matrix and why we need it. And I hope this is clear. Okay, so this is how we get the, and so what Abe was saying that it should be two, or Abe or Kartikeya, I forgot who, but yeah, one of them was saying since it is I think Kartikeya was saying that it is 2 cross 2 matrix, so it must be 2 cross 2 matrix for the linear transformation, but that is not the case because the basis element has 4 element in domain and similarly in the codomain. So corresponding matrix of linear transformation will be 4 cross 4, even though the linear transformation itself is from 2 cross 2 matrix to 2 cross 2 matrices. Any doubts? I mean, we will solve the example and you will get the idea overall. So let us start with this question. I guess we are now in question 5. Okay, so question 5. So let T from R2 to R2 be a linear transformation. So we are already given that it is a linear transformation, so we need not check it. Defined by T of x comma y equal to x plus y comma x minus y. Okay, and now I want to find, so for first question they are giving to compute corresponding linear transformation matrices. Okay, so they are given beta, the standard basis in R2. So the beta is the basis of domain, which is 1 comma 0, 0 comma 1, the standard basis of R2. And this gamma is what? What is it? Yeah, it is 1 comma 0 and 1 comma 1. Okay, so this is now what I want to find is compute T beta gamma. So how to solve this? So this T beta gamma will contain what? So if I write this as beta 1, this to be beta 2, this gamma 1, this gamma 2. So this row will correspond to T beta 1, sorry, this column will correspond to T beta 1, this column will correspond to T beta 2, and the corresponding rows will have the coefficients from gamma 1 and gamma 2. So how to do it? So we are starting with beta 1. Okay, so let us compute the T of 1 comma 0. And what is it? T of 1 comma 0, and it is 1 plus 0 comma 1 minus 0, and it is what? 1 comma 1, right? And now I want to write this in the linear combination of gamma. Sorry, yes. So if I want to write this as a linear combination of gamma, then how will I write this? This is what? 1 into 1 comma 0 plus 0 into 1 comma 1, right? Any doubts here, like what I'm doing? This is linear combination in gamma of the gamma. So whatever image I'm having in W, so this is basis of V, this is basis of W. So I started with the element from the basis of V, and I'm going to W now. So this was in the basis beta 1, and now we are in W now. So I will write this image in the terms of basis 1, 0, 1 minus 1. 1 plus 0, 1 minus 1. Yes. Oh, 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 oh. No, 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 no. X plus Y. So this is beta 1. T beta 1, which is T of 1 comma 0. And see, this is 1 comma 1. So I want to write 1 comma 1, 1 comma 0. So forget this. Okay, so I have this. So now I want to consider this, and I want to find this A gamma 1 and B gamma 2. That is A, what is gamma 1? It is 1 comma 0 plus what is gamma 2? It is 1 comma 1. And if I compare, what I will get? A to B. So these imply what? A is 0 and B is, sorry, A is 1 and B is 0. So keep this in mind. So the corresponding, so I am writing here T beta gamma. The corresponding coefficients of the first row correspond to T beta 1. Okay, so here I will get 1 and here I will get 0. Here we had gamma 1, gamma 2, T beta 1, T beta 2.
Sorry, I did not get where we came from 1 plus 0 comma 1 minus 0 to
So it is the
1
definition
comma
of,
0.
this is the definition of our T, right?
How it is 1 minus 0 is 0? I'm not getting that.
Oh, okay, okay, okay. I wrote 1 minus 0 to be 0. Okay,
Yeah,
sorry, sorry, sorry. Sorry. So it will be now 1, 0, and here it will be 1. So A will be 0 and B to be 1.
okay, this seems fine.
Yeah, yeah. Okay, sorry, sorry. Sorry, really sorry. I just wrote 1 plus 1 is 1 and 1 minus 0. Okay, 1 plus 0 is 0. Sorry, 1 plus 0 is 1 and 1 minus 0 is 1. Thank you very much, Jackie. Thank you. So is this clear now? Now there is no doubt, I guess. Any doubts?
So 1 comma 1 would be equal to A gamma 1 plus B gamma 2. There also it should be changed to 1, right?
Yes, yes. Here it will be 1 comma 1. Yes. And now this is clear. A will be 0 and B will be 1. And corresponding linear combinations I'm writing here. So coefficient of gamma 1, I need to put it in the first place and the coefficient of B to be in the second place. So it is 0 and 1. Any doubt for the first column? No. So we will, no, right? Okay. Even Abe said that he does not have any doubt. So let us move to second element. Second one is T of 0 comma 1, which is now 0 plus 1 comma 0 minus 1, which is now 1 comma minus 1, right? Yes. And now I want to write this 1 comma minus 1 in terms of a, let us say, gamma 1 plus B gamma 2. And which is what a gamma 1 was? 1 comma 0 and gamma 2 is, what is it? I think 1 comma 1. Yes, gamma 2 is 1 comma 1. And if you do all this linear combination thing, you will end up getting that it will be or let me just write a plus b is equal to 1 and second one is just minus b is equal to minus 1, so b is equal to 1 and what I'm getting a plus b is equal to 1, then a, am I doing something some mistake here? No, or am I? B is equal to minus 1, it's not minus b, it's b is equal to minus 1 and then this will imply that a plus b is it has to be 1, then a will be 2. Okay, so in this case we are getting a to be 2 and if I want to write this matrix here, then what I get here, now I want to write a here, oops, a here and b here. So this is linear transformation matrix of this t. So this is t. These are our bases beta and gamma, and corresponding to it, I am getting this linear transformation matrix. And anybody who know that what this linear transformation matrix actually does? So what this actually means? So this is linear transformation matrix. So can we find the rank of the transformation by finding the rank of this matrix, right? Yes. So here it is 2. And if you find the rank of this linear transformation also by rank nullity theorem, it will be 2 again. Okay. So anybody know like what this matrix actually signify? So I am saying that this is with respect to beta and gamma. So let us try to evaluate. So what my t was x comma t is from R2 to R2 such that x comma y is going to x plus y and x minus y, right? And what I got is here t with respect to this beta and gamma. So if I find out this, multiply this t beta gamma and corresponding vectors, say 1 comma 0, then what I will get? 0, 1, 2, minus 1, and I multiply this by, and what this is? This will give me 0 and 1. And if I find out the linear transformation, and if I find t of 1 comma 0, what it is? 1 comma 1, right? But what I'm getting here is 0, 1. But what this was, when I wrote this matrix here, this coefficients, I mean these rows were obtained from the coefficients of gammas. So this first was indicating the coefficient of gamma 1 and this was indicating the coefficient of gamma 2. So corresponding to this matrix here, what I have is 0 into gamma 1 plus 1 into gamma 2 is what? 0, 0 plus whatever the gamma 1 is, it will be 0, 0 plus 1 into gamma 2 was 1 comma 1. And this is what? 1 comma 1. So under the linear transformation, this image of 1, 0 is actually giving me 1, 1 again. Okay, so when we get this image, it is actually the coefficients of gamma 1 and gamma 2, which we need to put to obtain the image of T in W under the basis gamma 1 and gamma 2. Change of coordinates, exactly. Take the basis elements of V to the basis elements of W. Exactly. So when we have the linear transformation matrix, linear transformation identity linear transformation, that is V going to V. In that case, if we have two different bases, suppose beta 1 and beta 2, and when we find the linear transformation matrix of that linear transformation, the identity linear transformation with respect to this beta 1 and beta 2, then what we get is basis change matrix. And what we got here is actually linear transformation matrix with respect to different bases. And now we change so we are keeping the map same. And now we will change. So this was first. Okay. So I'm keeping the linear transformation to be same. T from M to R2 to R2. Again defined by T of x comma y to be x plus y comma x minus y, right? And now I'm taking this alpha to be, is it 2 comma 1, 1 comma 2, and beta to be what? 1 comma 0. So not beta, the gamma. And I want to find the linear transformation matrix. Compute, or let me write compute T. Now my basis in the domain is alpha, and in W or the codomain is again gamma, which we had earlier also. So now what we have, so alpha is this. So we will start with T of 2 comma 1. And what is T of 2 comma 1? It is 2 plus 1 comma 2 minus 1. So it is 3 comma 1, right? So now this 3 comma 1, I want to write as the linear combination of A1 comma 0, the gamma, the linear combinations of gamma, plus beta of 1 comma 1. Let me write linear combination of gamma. Okay. So what we will get? A plus B is equal to 3 and 1 is equal to B. So and A will be 2. So my this T alpha gamma has first column 2 and 1. The coefficients of gamma 1 and gamma 2. And what is T of 2 comma 1? I want to look for now second column. So it will be 1 plus 2 comma 2 minus 1. Oh, sorry. 1 minus 2, and it will be now 3 comma minus 1. And then I will be writing it again as linear combination of gamma 1 and gamma 2. And in this case, if you check, I will get A to be 4 and B to be minus 1. Okay, same pattern. Or let me write A plus B will be 3 here, and B will be minus 1, and B, once we have minus 1, I will get A to be 4. Then now the second column here becomes 4 minus 1. And what this signify here? So now I have this T alpha gamma, which is, I get 214 minus 1. Now what I do is, I take this T, take alpha beta, and multiply this with this 1 0. What I will get is 2, 1, 4, minus 1. And this is or 1, 1. So it will give me what? 1, 1. So it will give me 2 plus 4, 6, 1 minus 1, 0. And corresponding to this element, what we have in W is 6 into, in gamma, 6 into 1 comma 0. 6 into 1 comma 0. So which is what? 6 comma 0. But here also, it is not image of 1, 1. It is image of actually, we are now in the alpha. When I am writing this 1, 1, it corresponds to the element 2 comma 1 plus 1 into 1 comma 2, which is what? 3 comma 3. And if you see that T of 3 comma 3 is actually 6 comma 0. So this is what this linear transformation matrix actually represent. Any doubts here? This is not the image of 1, 1 is equal to 6, 0 as a image of linear transformation. No, it is not. When I write this, I mean the coefficients of, here when I write 1, 1, these are coefficients of alpha. And when I get this 6, 0 here, this is coefficient of gamma. Any doubts here? Like why we have this linear transformation matrix and how the basis play a role when we obtain this matrix? Please let me know any doubts. Okay, so I assume everybody understood everything. If you want to ask anything related to this, please feel free to ask. If not, then I would like to. Yes, okay. Abe said that he understood. So we'll move to the next question. So now we were in this R2 into R2 kind of stuff. We will now go to this question. Suppose let T be from R2 to R3 be linear transformation. Just a second. Defined by T of x comma y going to x minus y to x comma x plus y. Okay. Now we will see like how things are here. Now suppose now beta b again 1 comma 0, 0 comma 1, the standard basis in R2, and gamma is, let us take this 1 comma 0 comma 1, 0 comma 1 comma 1, and minus 2 comma 1 comma 0. And we need to compute T beta gamma. Again, we will have to do the same thing. We have to find T of beta 1, which is now, let me write here beta 1. This is beta 2, gamma 1, gamma 2, and gamma 3. T beta 1 is T of 1 comma 0, which is x plus x minus y. So 1 minus 0, 2 into 1, comma, right? Yeah, 2 into 1, comma 1 plus 0. So it is 1 comma 2 comma 1. And now this 1 comma 2 comma 1, I want to write it as linear combination of this gamma. So A gamma 1 plus B gamma 2 plus C gamma 3. And what this will be A 1 comma 0 comma 1 plus B 0 comma 1 comma 0 plus C minus 2 1 comma 0. And then we will get this A minus 2C, B plus C, A plus B, and then we get A minus 2C is equal to 1. I'm just comparing now components. B plus C is 2 and A plus B is what? 1. So from here I get A to be 1 minus 2C. From here I get B to be 2 minus C, right? And from here, if I substitute this AB, then 1 minus 2C plus 2 minus C, I get this to be 1, right? So, and when I compare, I get what I get? Minus 3C is equal to 1 minus 3. So, C is equal to what? Or am I making some mistakes? Oh, here it is plus. Plus C minus 2. So, it is C is equal to 1 minus 3. So, it is minus 2. Okay, and when I substitute, I get 1 plus 2C. It is 1 plus 2 into minus 2, which is 1 minus 4, which is 3 minus 3. And B again I get to be 4. 2 minus minus 2 is 4. So this T alpha beta or beta gamma? Okay, beta gamma. Beta gamma is now what? 3 cross 2 matrix. 3 cross 2 matrix with coefficients A is minus 3, B is 4, and C was minus 2. And similarly, I need to find the coefficient of T1 comma 0, which is now 0 comma 1. This is corresponding to T beta 1. This is T beta 2. T1 minus 0, 2 into 0, and 0 plus 1. So it is 1 comma 0 comma 1. Or it is also, sorry, x minus, so this is this element. And again, I want to write this minus 1, 0, comma 1 as a linear combination of A gamma 1 plus B gamma 2 plus C gamma 3. And when you substitute at the end, you will get again A minus 2C, B plus C, A plus B. So LHS here will always remain the same because A are just scalars which we are giving the numbers to in variables which we need to find, and gamma 1, gamma 2, gamma 3 are anyway basis elements which are ordered. So this term will always remain the same. And you can check that, okay? You just solve this and you will get this, and corresponding I get A minus 2C to be minus 1, B plus C to be 0, and A plus B is what? 1. So from here again, A is equal to minus 1 plus 2C. From here, B is equal to minus C. And from here, what I get? Again, A plus B is minus 1 plus 2C plus minus C is equal to 1. And I end up getting C is equal to 2. Okay, because 2C minus C is C. And this, when I shift this 1 there, I get C is equal to 2. And this will give me A is equal to minus 1 plus 2 into 2, which is 3. And B is now minus 2. That's it. And so this matrix here becomes now substituting these ABCs here is 3, minus 2, and 1. Right? No, 2. And when you again substitute or try to find and multiply this matrix by 2 cross 2, then T gamma beta, you have to multiply. So this is 3 cross 2 matrix. The elements in R2 are of the form AB. Corresponding matrix you will again get, this is 2 cross 1, so you will get 3 cross 1 matrix. Suppose we call it PQR. Then this PQABs are linear combination coefficients. So this will be A beta 1 plus the T of A beta 1 plus B beta 2 is equal to P gamma 1 plus Q gamma 2 plus R gamma 3. This what this matrix represent. Okay, any doubts here? Any doubts? Oh, okay. So you got the idea, like how these linear transformation matrices are obtained and how what significance they have and how to find them. Okay, so one last question which we do now is okay. Now we again find the linear transformation of this matrix. Just a second. Let this was third question, right? This will be the last one. Let T from R2 or let us say R3 to R2 such that x comma y comma z defined by Tx comma y z going to x plus y comma z. Okay, we will again try to solve. So here it was 3 cross 2 matrix. Now since we are going from R3 to R2, it will be 2 cross 3 matrix. Okay, and now let us take beta to be standard basis of R3 and gamma to be this 0 comma 1 1 comma 1. Okay, so we want to find again the matrix linear transformation. So in the exam they need not actually ask you to compute or find the exam entire matrix. Okay, they will ask you to give the exact entry. Okay, that give the first or 1 comma 1 entry of t beta gamma or 2 comma 2 entry of t beta gamma or 3 comma. So in this case, if you by any mistake end up writing this, for example this t beta gamma needs to have this thing that t beta 1 t beta 2 and this needs to be coefficients of gamma 1 gamma 2 and gamma 3. Okay, by any mistake, if you end up writing this like this, that I will write t beta 1 here, t beta 2 here, and I will write coefficients like this, gamma 1, gamma 2, and gamma 3. And even if you change the orders of gamma 1 and gamma 2, this matrix will change. Okay, when we find the linear transformation matrix of given linear transformation, the basis which we considered are ordered basis. That is, we are giving the order to this basis elements. So first basis elements needs to be the coefficient of it needs to be written in the first row itself. Okay, you should not change it. Okay, so if it is like m cross n matrix, in that case making such mistake would be very less, but in case of 2 cross 2 or n cross n matrices this could happen. So please be very what I can say, keep this in mind clearly. T should be vertical and coefficients should be horizontal, something kind of, you make a trick and remember it. So we will start obtaining, so finding basis for this or the linear transformation matrix for this. So it will be 1 comma 0. Oh, yeah, 1 comma 0. And how can I write 1 comma 0 here? It is, I'm just directly writing, it will be minus 1 0 comma 1 plus 1 1 comma 1, right? You can check this because this will be what, 1 plus 1 plus 0, 1, 1 minus 1, 0. So this is my first coefficients. Directly I got the linear transformation. The linear combination. Linear combination, again I'm writing it so that it will be clear for you. Linear combination of gamma. Similarly, again it will be 1 comma 0 and it is minus 1. Okay, minus 1. Again similar 0 comma 1. 1 into 1 comma 1. And the last one t of 0 comma 0 comma 1, and now this is 0 comma 1. And this is what 1 into 0 comma 1 plus 0 into 1 comma 1. So my corresponding matrix will be T beta gamma. First it is T, let me write beta 1, T beta 2, T beta 3, and here gamma 1, gamma 2. Okay. So first coefficient is minus 1, 1. Here minus 1, 1, and this one is 1, 0. Okay. Any doubt here? And what is rank of this matrix? Anyone would like to guess? 2. Jackie said that rank of this matrix is 2. And if you calculate this linear transformation and obtain the rank by rank nullity theorem, you will again Karthikeyan also said that rank of this matrix is 2. So what again Karthikeyan was asking me that can we find the rank using, okay, not Karthikeyan, I think Abe was asking whether I can find the linear transformation matrix and obtain its rank, and then yes, Abe was asking. Then can we talk about the the rank of a transformation using the linear transformation matrix? So you can see here that the rank of this matrix is 2, and rank of this linear transformation, if you calculate using rank nullity theorem and so on, it will again be 2. Okay. And similarly here also in this case, if you go and find, you will get that rank will be 2 and so on. So any doubts here, like how we are doing this and all? Any doubt from the entire session which we had today, from first to last? Any doubt where you felt that this was a bit unclear? Please, if you have any such doubt, please let me know. Okay, so I will just quickly go through everything. So this was the first question was about the linear transformation, how to find it. And this was the theorem which we used, that T of V1 plus CV2 is equal to T of V1 plus CTV2 to check all the linear transformation which we obtained. And this was because of the lemma which we proved that checking this condition is enough to check whether the given map is linear transformation or not. And the second question which we dealt with was how the basis behaves, or spanning set or linearly independent set behave when we go from basis or a set from V to corresponding TB, the set of images. And we saw that if B is any given set such that its image is linearly independent, then B becomes linearly independent. However, if B is linearly independent, then TB need not be linearly independent. Also, if B is a spanning set, the TB need not be spanning set. And using these two, we got that if B is a basis, TB need not be the basis. We saw the example which was linear transformation, which was giving us trivial counter example for these statements. And we also gave two non-trivial examples where the basis was not going to basis because of one was lacking linear span, the other was lacking linear independence. The next question which we saw was related to whether the linear transformation is injective or not. And okay, this was, yeah. So we say that T will be injective if and only if the null space contains only one element, that is 0. That 0 is the only vector which goes to 0. Then T will becomes the injective linear transformation. And further, we saw the rank nullity theorem, the null space, definition of range, dimension and rank, and dimension theorem, which says that dimension, if T is linear transformation from V to W, and V needs to be a finite dimensional vector space, then dimension of V is rank of T plus nullity of T. Note that here the dimension of W is not mentioned because we do not need the dimension of W. In this case, we only need the dimension of V. Then we went through few questions where we found, calculated the rank and nullity of given linear transformation. And yes, and finally we worked with the, yes, and before that we also went through this question, this map which we defined here corresponding to 2 cross 2 matrix, where this map is defined like T sub A B goes to A multiplied by B in the matrices M2R, and we proved that this linear transformation, this map, it gives linear transformation for every given matrix A. And also we show that if TA becomes a zero map by any chance, then only possible choice for A would be zero matrix. Okay. No non-zero matrix will give me TA to be zero map. And finally, we learned about the linear transformation matrices, like how to calculate them and what exactly they represent when we multiply or obtain the images using the linear transformation matrices with respect to given basis. Okay, and I hope make sure that when you write the columns, they corresponding to the images, and when we write images of the domain and corresponding coefficients in the rows. Okay, keep this image in mind where I wrote that. Yes, or let me write this here. This needs to be like TV1 entire row, TV2 entire column, so on, TVM, this entire row. And coefficients are the gammas, the coefficients from the basis of codomain. Okay, make sure to write it properly. And we solved few questions where we calculated the linear transformation matrices of few linear transformation. One where both the domain and codomain had same dimension, one and two where they had the different dimensions. Okay, and we also understood that finding the rank of linear transformation matrix is equivalent to, or not equivalent, but is giving us the rank of a matrix, rank of the linear transformation T. Any doubts? Okay, nobody's asking for any doubts. Then I guess we can stop here. You can ask the doubts in the discussion forum, and these notes and this recording of this lecture or this live session will be available in the problem solving session tab in the SWAYAM portal. Okay. Thank you. And okay, yes, Jackie, the notes will be available in the portal of the SWAYAM, and recording of this video will also be available in that portal. Okay, and okay, that will be available on the portal. Okay, I can't share this on the chat because I need to make a few changes here. But yeah, the notes will be available in the portal, video recording. If you have any doubt, you can go through it again using the video, and that's it. And next week we will meet again at the same time, 3 p.m. on Saturday. Okay, thank you very much. See you all next week. Bye.